Alright guys, so there is a lot to go over for the science notes this week, but they actually kind of complement the math. So we're going to be talking about data, collecting it, interpreting it, how to show it on paper. So data, it's just another fancy word for information, the truth, facts, numbers, things that you were able to count and verify and observe. It's the information that we use to make decisions and make conclusions, okay? So first off, collecting and interpreting data. Data is collected for many reasons. This is an important step in the scientific process. So why do we collect data? Every time an experiment or study is conducted, data is collected. It is then used to make conclusions and determine the results of the experiment. How do we collect data? There are many ways to collect data. Collecting data can be as simple as asking several people the same question. For example, you might ask your classmates which color is their favorite. You might collect data by measuring something. You might use a ruler or a thermometer to collect data. If you wanted to find the effect of water on the growth of a plant, you could measure the plant's growth. This would be collecting data. You might also read books to collect data. You might observe something and write down what you see. Writing information down is an important part of collecting data. How to organize and display data. Often, when data is collected, it is recorded in a tally chart. So that's where you have like your little 5, 1, 2, 3, 4, 5, where you're counting things. This is a simple way to organize the information. This could be used if you asked your classmates about their favorite colors. You could record a tally for each person selecting a certain color. Why would we do that? Because organized data is so much easier to use than just numbers and words all over the place. So another way to organize information is to record it in a table. You could use this if you were measuring a plant's growth. You could record the information in a table each time you measure the plant. So I'm not talking about a table like you put your food on it, but something where you have like day and height, if we're talking about a plant. Day 1, it's 1 inch. Day 2, it's 2 inches. Day 3, maybe it's 4 inches. Day 4, let's say that it is 8 inches. It's doubling every day. That would be a table. You have one thing and another piece of information on the other side. But they both rely on each other. Displaying data. After data is collected and organized, it is often displayed in a graph. This makes it easier to compare, interpret, and analyze the information. There are several different types of graphs that can be used. Each has a specific purpose. Some common ways to display data are with bar graphs, pictographs, line graphs, line plots. You can see Saxon Investigation 4 to learn about line plots, pie charts, and Venn diagrams. So first we're going to talk about bar graphs. Bar graphs are a way to display data that tells how many of something. So this would be quantitative. But it could also be qualitative. You know what? I'm going to leave that alone for now because it depends on what the data is that you're collecting. If data was collected to show how many of a certain animal lived in the woods, the information could be displayed in a bar graph or a pictograph. This is qualitative for this example. So how many bears, how many deers, how many rabbits, how many wolves, how many badgers. Each of these are a quality, each of these are a category, and we're saying how many they are. This is qualitative data shown in a bar graph because those are bars. A pictograph uses pictures to show how many there are of something while adding a visual interest. So bears, 1, 2, and about a half. What does that tree mean? Oh, it says each tree represents 10 of that animal. So how many bears are there? 10, 20 and a half, 25. 10, 20, 30, 40 and a half, 45. 10, 20, 30, 40, 50. 10, 20, 30. 10, 15. Let's see if that matches up with this information. 10, 20, about a half, 25. 10, 20, 30, 40 and a half. 10, 20, 30, 40, 50. 10, 20, 30. 10, and 15. So I had 25 bears, 45 deers, 50 rabbits, 30 wolves, and 15 badgers. So this bar graph and this pictograph are telling me the same exact information, but this one is doing it with some bars, which, I mean, for adults, just, you know, trying to get some basic information, bar graphs are cool. But for everybody, anybody who wants to have something with just a little bit more interest in there, something more fun to look at, then you can put little pictures. They could have put a little bear. They could have put little deer for that one, but then they'd have to do a legend that says a bear shape represents 10 bears, a deer represents 10 deers. So trees works out because they all live in the forest. And so we're saying the same information, it's just that this one's with cool little trees, that one's with little colors, bars. A line graph can show change over time. If you recorded your height each year on your birthday, you could use a line graph to show your change in height over the years. So height in inches and somebody's age in years. And it's showing like in that first year since they were born, they went boom. They went from like a little baby, like nothing, up to boom, 30 inches. That's 2.5 feet. And then they grew some more, grew. Let's see, right about here is about 4 feet. They hit 4 feet when they were about 6 or 7 years old. And let's see, 60 inches would be 5 feet. So they'll eventually hit 6 feet, 5 feet, whatever you want to call it. Same difference, right? 5 feet is coming up right there. So this person is growing, and they're growing at their own rate. Pie charts. This right here, it looks like a delicious pizza pie, minus the pepperonis. Pie charts show parts of a whole. Percents are parts of a whole. If data was collected to show the percentage of voters selecting each candidate, a pie chart might display the data. So Smith got 39% of the votes. They get just over a third of that pie. Whoever this Bennett person is, 46%. That's really close to 50%. 50% is half. So Bennett should be really close to half, which they're really close to half. Croft gets about 15%. So depending on what percentage of the votes, what percentage of the whole something is, it colors in that percentage of a pie chart. And the last one that this wants to talk about is Venn diagrams. So often Venn diagrams are used for science and English and just comparing things. But Venn diagrams are excellent tools for organizing items based on their traits. Each trait is represented by a circle. An item that has a particular trait is listed inside the circle for that trait. An item that has more than one of the traits is listed in areas where the circles overlap. So this is saying 4 legs is one trait, fur is another trait, and a tail is another trait. So let's see, what things have a tail and fur, or what have a tail? Birds, monkeys, dogs, lizards. They all have tails. What else has a tail? Only 2 legs and no fur. Or tail, 2 legs, and fur. Well, a monkey. That's a good one. A dog has all these things. A lizard has 4 legs and a tail. Yeah. Let's see, what about a fish? Where would that fall? They have a tail. Do they have fur? No, they have scales. Do they have legs? Fish normally don't have legs, they have fins. So I'd put a fish in here. What has fur, but maybe doesn't have legs or tail? You know, I can't really think of any off the top of my head. Do bats have legs? They have wings. Yeah, they have little legs. They have little feet that grab onto things. So, yeah, they have legs, but they don't have 4 legs. I'm going to put a bat right here. So, a little flying bat. Let's see, 4 legs, but does not have fur or a tail. 4 legs, fur, no tail. 4 legs. I'll let you guys think on that one too. Maybe I'll think of something later. How to interpret data. Once your graph is created, the data is much easier to interpret. The graphs can clearly show how much a plant grew or how many people selected a certain color as their favorite. From this information, conclusions can be made about the data. This is how the results of the study or experiment are determined. The data can be used to explain why certain results occurred. If a bar graph is used to show people's favorite colors, it will be easy to see which color was chosen most often. The bar by that color will be the longest. By finding the shortest bar, you will be able to tell which color was chosen the least. So without even looking at the numbers, I can see that this is the shortest one, so it was the least. And I can see that this is the tallest one, so it was the most. And then if they ask me a question like, well, what color had the most votes? I would say, oh, blue. And then it might ask, how many votes did it get? Then I can go across here. Oh, it had 11. What was the least? Well, it was green with 2. What's my range? Well, it's from the lowest to the biggest. 2 to 11 was my range of options. So my other 2 colors, those should fall in between. Well, I've got a 4 and I've got a 7. So 4 is between 2 and 11. 7 is between 2 and 11. So everything fits within my range that I picked. If a line graph is used to show the growth of a plant, you will easily be able to see whether the plant grew or not. If the plant grew well, you might conclude that it had enough water or sunlight. If it did not grow, you might conclude that it needed to be cared for differently. So a line graph of a plant would look kind of like that picture that it used for a child growing and how they measured it every year. It's going to grow kind of like that. Maybe flatter, maybe lower, but it's probably not going to get shorter. Data can tell many things about an experiment or observations. So sometimes we can actually find patterns in our data. And that's one good reason to put data in pictures, is so that you can more easily not just calculate the pattern, but actually see the pattern with your eyes. So by looking closely at patterns in data, it is possible to predict what the next set of data will be. Consider this line graph showing basketball game scores for the Prairie Dogs. So right here, at the very beginning of the game, they had 0 points. Number of points, quarter. At the first quarter, they had, let's call that about 25 points. And then they played some more. Into the second quarter, they've got 50. Then they keep on playing, playing hard, doing a good job. And we're now at, in between 70 and 80, that's about 75 points. Are you noticing a pattern yet? They got 25 points. And then this is their total score. So they got some more points, and they have 50 now. Then they got some more points, and now they have 75. How many more points did they get each time? Well, 75 minus 50 equals 5, 2. Plus 25 points. Okay. 50 to 25. Oh, that's also 25. So each time it looks like, well, 0 to 25, that's plus 25, right? So they got 25 points, 25 points, 25 points. If you had to guess, if this team keeps on playing just as well and the other team keeps on playing just as well in exactly the same way, what would you make a wild guess? You may not be right, you may not be wrong, but what do you think it would probably end up being? Why not 75 plus 25? Probably about 100 points. So what change happens between the first number and the second number? We saw 25 points. Does the same change happen between the second number and the third? Yeah, it does. It keeps repeating. In order for there to be a pattern, the same number has to be added or subtracted from, or multiplied and divided by, every number to get the next number. So we have some questions coming up. After you find the pattern, you can use it to predict or make a guess what will happen based on the evidence you have, what the next data point or number will be. So practice question 1 wants to know, every quarter, the team score increases by how many points? So go back up to your graph, figure out how much it changes each time, and that answer is going to go right there. Practice question number 2. At the end of quarter 3, the team has blank points. So find quarter number 3, find how many points they have. This means that if their score increases according to the pattern, you can predict that they will have how many points at the end of the fourth quarter. So that was, they get the same amount every turn or every quarter. What's going to be their final number? So make sure to fill these in because these are required. Okay, so predicting outcomes without a pattern. So it's also possible to make a guess that makes sense, even when it is not possible to predict exactly what the next set of data will be. So questions to consider. Are all the numbers close to each other? If all the numbers are almost the same, it is easy to make a good guess about what the next number will be. Just look at the other numbers and choose a number that is close in number to all the other ones. Are all the numbers going up or are they going down? If all the numbers are going up, a good guess is that the next number will be higher than the last number. If all the numbers are going down, a good guess is that the next number will be lower than the last number. Okay, so what's that saying is if you have maybe a line graph for over time, if it's already going up, you can guess it's probably going to keep going up. If it's already going down, you can guess it's going to keep going down. Unless there's something else acting on it to change it, then we can assume that it's going to keep doing what it's doing. That's kind of like inertia that we learned about in science, in physics. So this table right here shows the amount of rain that Simpletown has gotten in each of the last 4 years. In 2005, they got 16 inches. 2006, they got 17. 2007, 15 inches of rain. And in 2008, they got 18 inches of rain. So practice question number 3. I want you to predict how much rain Simpleton should get in 2009. Hint, your answer will be a range. So Simpletown will likely receive between blank and blank inches of rain in 2009. So look at these numbers, 15, 16, 17, and 18. Those are all pretty close. They're within one of each other, and a total of 4 between the whole set. So I would say that next year, they're probably going to get a similar amount of rain. Any of these numbers would probably be reasonable. I don't know, like their whole entire history of the world, how much rain they get, but I know for these past 4 years, they've gotten between this much and that much. They've gotten somewhere in this range of rain. So I'm going to say my lowest number here and my highest number here. And that is my range. So I'm not going to put those numbers in for you, but they're right there. Pick the lowest number, put it here. Pick the highest number, put it there. That's all you've got to do. That's your range. So other questions you should consider. After completing an investigation, scientists often form new questions about the original subject. The new questions often build upon the knowledge that the scientists gained from the first investigation. Some possible new questions include, Can the investigation's procedure be improved to produce better results? What would happen if a different variable were tested? For instance, what if plants in an experiment were given different amounts of water or sunlight instead of different amounts of fertilizer? Are there new investigations that should be performed based on the current results? So this is kind of like our engineering design that we talked about a little earlier in, I want to say April, maybe May? Yeah, it was April or March. So experimental design. You decided what your problem was, you tried to find a solution to it, you test your solution, and then you think, could the solution have been better? You do an investigation. For this right here, you're doing an investigation. You look at the data, you look at your experiment, you look at your results, and then you decide, is there something I could have done differently? Is there something I could have done better to find a better answer, to find more information? So is there something else that I can think about? Is there something else that I can experiment with? Is there something else I can research that will help me to find out the best information about what I'm looking at? So sometimes a conclusion cannot be reached from the data obtained during an investigation. Perhaps the data did not show any pattern or trend. In such cases, it is possible that more than one variable determines the result. To find out, the scientist should design a new investigation to show how a particular variable affects the outcome of the investigation. Okay, so right now, there's a whole bunch of stories going around about how coronavirus can be treated with this or that or that or that. They've had some doctors give some people some medicine in one set situation, and in some cases it worked, some cases it didn't work. But those are only a couple cases. Until they've tested it on very many people, on a lot of different situations, they don't know for sure what is the best solution. Okay, so just because you hear a news report that says that such and such has cured 30 people of corona, we don't know for sure until we've cured 30 more and 30 more and 30 more. Those first 30 may have just all been lucky and been on something else in addition to it. They may have been already getting better. There may have been all sorts of other things going on, okay? So what has to happen is one set of scientists or doctors figures it out the first time, and then another set of doctors, another set of scientists does that same test, and they get the same results. If we keep seeing the same results, then we're good. If we don't keep seeing the same results, then something is different, something is not accurate. But we need the data. We need to be able to see it and read it and know. Okay, reasonable answers. When making scientific measurements or calculations, it is important to do more than check the work. It is important to consider whether the results or the answers are reasonable. Making sure that results are reasonable includes checking two things. Are the results typical? Do the units make sense? Let me see, does it say that? Yes. So typical values. Typical just means what you would expect. What you should expect. Okay, so if I go in my fridge and I want to get a glass of milk, if I pull out the milk and it is, I don't know, blue, that is not what I would expect. Those are not typical results for my milk. I would maybe put the milk back in the fridge, close my eyes a little bit, rub them, get the, morning eye boogers out, maybe wash my face, and go back and look at that milk again and make sure it's still blue. If it's still blue, I'm going to ask somebody, excuse me, did you put some food coloring in this milk, or am I going crazy? And if someone else sees that the milk is blue and no, they did not put food coloring in it, then Houston, we have a problem. So if you see something that makes absolutely no sense and it's not typical, it's not what you expect, then there's probably something wrong with your data. Or there is some new data that you need to consider and there's a problem, okay? Either way, something's up. So typical values. If a person is measuring the height of her 2-year-old sister, she should expect to get a value close to the height of other 2-year-olds. If the value she measured was 60 inches, or 5 feet, she would know that she made a mistake in measuring, because that is not a reasonable height for a 2-year-old, right? So I don't even think all of my 5th graders this year are 5 feet yet. So if you've got a 2-year-old that's taller than some of my 5th graders, something is weird. Unless that 2-year-old really is that tall. But if you put a ruler up to her and you measure 60 inches, probably not right. Because this is probably you at 60 inches. And this is the little 2-year-old. Probably not 60 inches, okay? Put them on a teeter-totter seesaw. Yeet! Okay, whenever measurements are made or read, we can look at a typical value for similar things and decide whether the measurement values we are reading or making are reasonable. So this table over here shows values that a student recorded as he watched a basin, that's just a fancy word for a sink, fill with water. He measured the depth with a ruler every 30 seconds. So when he first turned on the water, or actually before turning on the water, 0 seconds, 0 inches of water. That makes sense. It's an empty sink. No water's in it yet. So, no water's in it. After 30 seconds, it's about 2 inches deep. After 60 seconds, it's 4 inches deep. So we got plus 2, plus 2. Now, we haven't changed the speed of the water, so it's still pouring out at the same speed. 90 seconds, we have 6 inches, so that's another plus 2. And this is going plus 30 seconds each time. 90 to 120 is 30 seconds. 6 inches to 11 inches, whoa, we just went plus 5. What happened there? When I think of a sink, I think of either something like that shape, or if this is calling it a basin, it's probably just a perfect rectangle. And a perfect rectangle, it should fill at exactly the same speed every time. If I'm thinking of my sink right here, it should actually get slower, or it should not get as deep for per unit time if it's this shape. So we're probably talking about one of these shapes. We're probably not talking about a vase or something like that. Okay, so the data here is showing this shape. This is a vase. This is a basin. This is a sink. So which value in this table looks like it is wrong? Which value does not follow the same pattern as the others? Remember to look for the pattern. Which one does not follow the pattern? Which one follows its own little thing? So what should you do if this is your observation, this is your investigation, and you were measuring 0, 2, 4, 6, you've got something shaped like this, and all of a sudden you get an 11. That one seems weird. Maybe give it another 30 seconds and see what our next value is. See if that one is 13 inches. Or see if it comes out to something like maybe 11 inches. No, wait, 10 inches. So see what ends up happening for another one. Could be one result, one option. The reasonable units. The student, oh, that's next. That needs to go down there. The student recorded how much water was in the basin every 30 seconds. It looks like the basin filled up 2 more inches every 30 seconds until the last measurement. At the last measurement, the student recorded that it filled up 5 more inches in 30 seconds. Unless that water flow was turned up, that is an unreasonable answer. if a person is measuring the height of a plant, we would expect to have a measurement in a unit of length, such as meters, centimeters, inches, or feet. I'm going to put a space in there for you guys. Using units such as pounds or kilograms, which describe mass and weight, would not make sense in measuring the height of a plant. They would not be reasonable. So if I'm trying to see, okay, well, how long is this pencil, since I don't have a plant right here in front of me? Well, it is 1, 2, 3, 4, 5, 6, 7, 8, 15. Pencil equals 15 grams. But it's in metric? No. Grams is going to tell me how much it weighs. It probably does not weigh 15 grams. It weighs 15, this is just telling me metric, but I know that based on this size, because it's about the size of my pinky, it is centimeters. So a pencil is about 15 centimeters. Centimeters measures length. This pencil, I'm measuring its length. So I need to make sure my units make sense. My units have to be reasonable. I also wouldn't want to say that it is 15 feet or 15 miles. Hey guys, I'm writing with a 15-mile long pencil. No, I'm not. 15 miles would be 8 times 5 is 40. 5, 9. 15 miles would be all the way from 90th Avenue all the way to downtown Phoenix. That is a long distance. That is not a pencil. That's a bunch of exits on the 10 freeway. Okay, reasonable units continued. It would also not be reasonable to count something, such as marbles or paper clips, and come up with an answer such as 38 inches. Or pencil sharpeners. So if I'm counting pencil sharpeners, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, and what are my units? We'll call this miles. No, it's not 12 miles. I have 12 sharpeners. Okay, so your units have to be reasonable for what you're measuring. It has to make sense. Don't make up just funny words because it sounds cool. No, do not do that. So checking to see if the units make sense will help to avoid errors in scientific measurements or calculations. Acceptable data range. Often in scientific investigations, there is an acceptable range of variation in collected data. That is, even if an experiment is performed exactly the same way, there may be very slight differences in the data recorded for different trials. For example, imagine that a student wanted to know the mass of a chicken egg. She decides to find the mass of a dozen eggs, and then calculate the average. Part of her data is shown in the table. So egg A was 40 grams, B 60 grams, C 55 grams, D 50 grams, and E 47 grams. So it looks like this is my low, this is my high. My range is 40 to 60 grams is my average, is my range, I should say. So my average would probably be somewhere in the 50 range. So based on the data shown, a range of measurements that would make sense for this kind of chicken egg would be about 40 to 60 grams, my low number to my high number. So question number 5, is 120 grams in the acceptable range of 40 to 60 grams? So if the student recorded the mass of 120 grams for an egg, twice as much as my highest value, would that piece of data be in the acceptable range? Well, it's 2 times the highest. Does that make sense? I don't think it makes sense. Probably not. So that's going to be a no. Because 120 grams is not a reasonable measurement, The student should perform another measurement if possible to find out if she made a mistake. So instead of just saying, no, that's impossible, this is absolutely not correct, I'm just going to get rid of it, maybe it would be best to keep that same egg that came out as 120 grams and weigh it again on that same scale. Because maybe you accidentally had 2 eggs on there. It happens. People get crazy. Maybe you put the egg down and then you were like, just resting your hand on there. Maybe you put your pencil down on the scale, which would not be a smart thing to do, but is something that could happen. So maybe there was just something that went wrong that made it seem like it was bigger than it really is. So weigh it again, try again, and maybe you'll get the correct result. Maybe you'll get 120 grams again. Maybe it's just a really heavy egg. In that case, maybe try comparing that egg to 2 eggs. See if they come about the same weight. Try holding the 120 gram egg in one hand. Okay, get a good feel for it, set it down. Take another 60 gram egg. Okay, yeah, this is really light. Maybe that number's correct. Maybe it's not. But the only way you can find out is by trying until you are certain and positive. And that is it for the science notes. There's going to be a test on this. I think it's 5 questions, super quick and easy. Get it done. This has been about 36 minutes for these notes. So I think you guys are ready. Good luck.